proofs are more involved than our first, and both use the formula for an area of a triangle. The formula itself is straightforward, but the proofs truly require understanding why it works in order to fully digest and appreciate their brilliance. I personally struggled with this until I found my aha moments. I almost had to laugh because things became so simple and so clear, I don't know how I missed it. So I created this video as a way to scaffold your understanding of these advanced ideas. Although our target is triangles, let's build our intuition, first with rectangles, then with parallelograms. Because a rectangle has 4 right angles, you likely know the area formula as base times height. So if the base is 12 and height is 4, then area is 12 times 4 equals 48 square units. Good, a parallelogram is like a rectangle, but the angles may not be right angles. Let's change our color to purple and shift the base of our rectangle to the right while keeping the top fixed, and we create an infinite variety of parallelograms. Could all of these somehow be related? Let's think about that. Returning to our initial rectangle, imagine extracting a corner and sliding it from left to right until it aligns perfectly with the opposite side. This cutoff piece forms a right triangle, specifically a 3-4-5 triangle. Notice the symmetry where the removed and added areas perfectly balance each other. Not only have we morphed our rectangle into a parallelogram, but we've also preserved the base length constant at 12 with our shifted triangle, ensuring the height remains 4. This transformation shows the parallelogram's area remains the same as the rectangles, emphasizing our takeaway that the formula for a parallelogram's area is consistent with a rectangle because their areas equate. And this reversible process suggests that any rectangle can potentially spawn an infinite number of parallelograms, depending on how you slide or flip the parts. Whether by shifting sides or swapping triangles from one side to another, the total area remains the same. The key but hidden component is calculating the height is crucial. It's the vertical distance between the parallel lines. Again, from our rectangle, draw a diagonal line across our rectangle, and we usher in the star shape, a triangle. Actually, 2 right triangles, each mirroring the other in terms of side length and area, where both share the same hypotenuse d. Euclid proved that if 2 triangles share the same sides, they are congruent and share the same area. In geometry speak, it is side, 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 or SSS. What happens if we apply the same diagonal division to a parallelogram? Depending on which diagonal we choose, the shapes of the resulting triangles might differ, but by the principle of SSS, their congruence remains intact. Even though parallelograms look different than rectangles, we have the same SS story for parallelograms, ensuring each triangle occupies half the area of the parallelogram. And then we can conclude that the triangle area for half a parallelogram matches the triangle area for half a rectangle with the same base and height, so the formula does not change. This allows us to conclude that these 2 different looking triangles have equal area because they are both 1/2 the area of the same parallelogram. Thinking out loud, but I developed my intuition by viewing this as one big family. Here's the mindset that simplified everything to me that I'm trying to promote. A given triangle can appear in many forms, but regardless of the shape, if we copy the triangle, we birth a parallelogram, and likewise, parallelograms can birth a rectangle where all family members share the same base and height. Let's practice this with 3 different triangles. First, we duplicate each triangle and create a parallelogram. And then, to button things up, we can create the rectangle that has the same base and height as the triangle and parallelogram. As we expect, the sizes for each rectangle look quite different since they originated from different triangles. But did they? Let's retrieve our original 3 triangles and notice they all actually line up perfectly, which indicates all 3 triangles have the same shape and area. Then what does that tell us about the areas of the parallelograms and rectangles? They must all equate. Let's confirm what we now expect by measuring these shapes on graph paper. Blue has base 12, height 4, so the rectangle and parallelograms area are 48. Black has base 5 and height 9.6, and orange has base 9.85 and height about 4.87, both producing area 48 for the rectangle and parallelogram within rounding differences. And of course, the triangle area is 1/2 times 48, or 24. So, this is my big aha moment, which motivated this video. Yes, I knew the formula for the triangle area is 1/2 times base times height. However, I never thought about the family behind the triangle, that because a triangle has 3 sides, each side can be a base, so it has 3 different bases, and thus 3 different heights. But because they all relate to the same triangle, their areas all equate. And then the family expands like rabbits because each of these bases and heights produce parallelograms and rectangles. This is not just a reminder of a formula, but a reminder that geometry is not just about calculations. It's about envisioning and understanding relationships. And these relationships enlarge our appreciation of math and its bigger picture. Wonderful. Keep these thoughts fresh, because our goal in the next video is to follow each of Euclid's historic steps and uncover more beauty hidden within a right triangle.